Chapter 23 of Astronomy, The Science of the Heavenly Bodies, by David Todd. The Program of a Great Observatory. The Mount Wilson Observatory has now been in operation about 15 years. The novelty in construction of its instruments, the investigations undertaken with them, and the discoveries made, the interpretation of celestial phenomena by laboratory experiment, and the recent addition to its equipment of a telescope 100 inches in diameter, surpassing all others in power, directs especial attention to the extensive activities of this institution, whose budget now exceeds $1 million annually. Results are only achieved by a carefully elaborated program, such as the following, for which the reader is mainly indebted to Dr. Hale, the director of the observatory, who gives a very clear idea of the trend of present-day research on the magnetic nature of the Sun and the structure and evolution of the sidereal universe. The purpose of the observatory, as defined at its inception, was to undertake a general study of stellar evolution, laying especial emphasis upon the study of the Sun, considered as a typical star, physical researches on stars and nebulae, and the interpretation of solar and stellar phenomena by laboratory experiments. Recognizing that the development of new instruments and methods afforded the most promising means of progress, well-equipped machine shops and optical shops were provided with this end in view. The original program of the observatory has been much modified and extended by the independent and striking discovery by Campbell and Kapteyn of an important relationship between stellar speed and spectral type. The demonstration by Hertzsprung and Russell of the existence of giant and dwarf stars. The successful application of the 60-inch reflector by Van Manen to the measurement of minute parallaxes of stars and nebulae. The important developments of Shapley's investigation of globular star clusters. The possibilities of research resulting from Sears' studies in stellar photometry. And the remarkable means of attack developed by Adams through the method of spectroscopic parallaxes. By this method, the absolute magnitude, and hence the distance of a star, is accurately determined from estimates of the relative intensities of certain lines in stellar spectra. Attention was first directed toward lines of this character in 1906, when it was inferred that the weakening of some lines in the spectra of sunspots and the strengthening of others was the result of reduced temperature of the spot vapors. On testing this hypothesis by laboratory experiments, it was fully verified. Subsequently, Adams, who had thus become familiar with these lines and their variability, studied them extensively in the spectra of other stars. In this way was discovered the dependence of their relative intensities on the star's absolute magnitude, so providing the powerful method of spectroscopic parallaxes. This method, giving the absolute magnitude as well as the distance of every star, excepting those of the earliest type, whose spectrum is photographed, is no less important from the evolutional than from the structural point of view. Investigations in solar physics, which formerly held chief place in the research program, have developed along unexpected lines. It could not be foreseen at the outset that solar magnetic phenomena might become a subject of inquiry, demanding special instrumental facilities and throwing light on the complex question of the nature of the sunspots and other solar problems of long standing. It is obvious that these researches, together with those on the solar rotation and the motions of the solar atmosphere developed by Adams and St. John, must be carried to their logical conclusion if they are to be utilized to the fullest in interpreting stellar and nebular phenomena. The discovery of solar magnetism, like many other Mount Wilson results, was the direct outcome of a long series of instrumental developments. The progressive improvement and advance in size of the tools of research was absolutely necessary. Hale's first spectroheliograph at Kenwood in 1890 was attached to a 12-inch refractor and the solar image was but 2 inches in diameter. It was soon found that a larger solar image was essential, and a spectrograph of much greater linear dispersion. In fact, the spectrograph must be made the prime element in the combination, and the telescope so designed as to serve as a necessary auxiliary. Accordingly, successive steps have led through spectrographs of 18 and 30 feet dimension to a vertical spectrograph 75 feet in focal length. The telescope is the 150 feet tower telescope, giving a solar image of 16.5 inches in diameter. Its spectrograph is massive in construction, and by extending deep into the Earth, it enjoys the stability and constancy of temperature required for the most exacting work. Another direct outgrowth of the work of sunspot spectra is a study of the spectra of red stars, where the chemistry of these coolest regions of the Sun is partially duplicated. The combination of titanium and oxygen, and the significant changes of line intensity already observed in both instances, and also in the electric furnace at reduced temperatures, give indication of what may be expected to result from an attack on the spectra of the red stars with more powerful instrumental means, which is now provided by the 100-inch telescope and its large stellar spectrograph. Other elements in the design of the 100-inch Hooker telescope have the same general object in view, that of developing and applying in astronomical practice the effective research methods suggested by recent advances in physics. Fresh possibilities of progress are constantly arising, and these are utilized as rapidly as circumstances permit. The policy of undertaking the interpretations of celestial phenomena by laboratory experiments, an important element in the initial organization of Mount Wilson, has certainly been justified by its results. Indeed, the development of many of the chief solar investigations would have been impossible without the aid of special laboratory studies, going hand in hand with the astronomical observations. So indispensable are such researches, and so great is the promise of their extension, that the time has now come for advancing the laboratory work from an accessory feature to full equality with the major factors in the work of the observatory. Accordingly, a new instrument now under installation is an extremely powerful electromagnet designed by Anderson for the extension of researches on the Zeeman effect and for other related investigations. Within the large and uniform field of this magnet, which is built in the form of a solenoid, a special electric furnace designed for this purpose by King, is used for the study of the inverse Zeeman effect at various angles with the lines of force. This will provide the means of interpreting certain remarkable anomalies in the magnetic phenomena of sunspots. The 100-inch telescope is now in regular use. All the tests so far applied show that it greatly surpasses the 60-inch telescope in every class of work. For many months, most of the observations and photographs have been made with the Cassegrain combination of mirrors, giving an equivalent focal length of 134 feet and involving 3 reflections of light. The 100-inch telescope is found to give nearly 2.8 times as much light as the 60-inch telescope, and therefore extends the scope of the instrument to all the stars an entire magnitude fainter. This is a very important gain for research on the faint globular clusters, as well as the small and faint spiral and planetary nebulae, providing a much larger scale for these objects, and sufficient light at the same time. Photographs of the Moon and many other less critical tests have been made with very satisfactory results. Those of the Moon appear to be decidedly superior in definition to any previously taken with other instruments. Another investigation is of great importance in the light of recent advances in theoretical dynamics. Darwin, in his fundamental researches on the dynamics of rotating masses, dealt with incompressible matter, which assumes the well-known pear-shaped figure, and may ultimately separate into 2 bodies. Roche, on the other hand, discussed the evolution of a highly compressible mass, which finally acquires a lens-shaped form and ejects matter at its periphery. Both of these are extreme cases. Jeans has recently dealt with intermediate cases, such as are actually encountered in stars and nebulae. He finds that when the density is less than about 1/4 that of water, a lens-shaped figure will be produced with sharp edges, as depicted by Roche. Matter thrown off at opposite points in the periphery, under the influence of small tidal forces from neighboring masses, may take the form of two symmetric filaments, though it is not yet entirely clear how these may attain the characteristic configuration of spiral nebulae. The preliminary results of van Manen indicate motion outward along the arms, in harmony with Jeans' views. Jeans further discusses the evolution of the arms, which will break up into nuclei of the order of mass of the Sun, if they are sufficiently massive, but will diffuse away if their gravitational attraction is small. The mass of our solar system is apparently not great enough, according to Jeans, to account for its formation in this way. As is apparent, these investigations lead to conclusions very different from those derived by Chamberlain and Moulton from the planetesimal hypothesis. This is a critical study of spiral nebulae, for which the 100-inch telescope is, of all instruments in existence, the best suited. The spectra of the spirals must be studied, as well as the motions of the matter composing the arms. Their parallaxes, too, must be ascertained. A photographic campaign, including spiral nebulae of various types, will settle the question of internal motions. The large scale of the spiral nebulae at the principal focus of the Hooker telescope, and the experience gained in the measurement of nebular nuclei for parallax determination, will help greatly in this research. A multiple-slit spectrograph, already applied at Mount Wilson, will be employed, not only on spiral nebulae whose plane is directed toward us, but also on those whose plane lies at an angle sufficient to permit both components of motion to be measured by the two methods. In dealing with problems of structure and motion in the galactic system, the 100-inch telescope offers special advantages because of its vast light-gathering power. Studies of radial velocities of the stars have hitherto been necessarily confined to the brighter stars, for the most part even to those visible to the naked eye. While some of these are very distant, most of the stars whose radial velocities are known belong to a very limited group, perhaps constituting a distinct cluster of which the Sun is a member, but in any event of insignificant proportions when contrasted with the galaxy. Current spectrographic work with the 60-inch telescope includes stars of the 8th magnitude and some even fainter. But while the 60-inch has enabled Adams to measure the distance of many remote stars by his new spectroscopic method, and to double the known extent, so far as spectroscopic evidence is concerned, of the star streams of Chaldea, a much greater advance into space is necessary to find out the community of motion among the stars comprising the galactic system. The Hooker telescope will enable us to determine accurate radial velocities to stars of the 11th magnitude, which doubtless truly represent the galaxy. In order to secure a maximum return within a reasonable period of time, the stars in the selected areas of Chaldea will be given the preference, because of the vast amount of work already done relating to their positions, proper motions, and visual and photographic magnitudes. Such consideration as spectral type, the known directions of star streaming, and the position of the chosen regions with reference to the plane of the galaxy are given adequate weight, and it is of fundamental importance that the method of spectroscopic parallaxes will permit dwarf stars to be distinguished from stars that are in the giant class, but rendered faint by their much greater distance. In addition to these problems, the stellar spectrograms will provide rich material for study of the relationship between stellar mass and speed, and the nature of giant stars and dwarf stars. Shapley's recent studies of globular clusters have indicated the significance of these objects in both evolutional and structural problems, and the possibility of determining their parallaxes by a number of independent methods is of prime importance, both in its bearing on the structure of the universe and because it permits a host of apparent magnitudes to be at once transformed into absolute magnitudes. Here, the advantage of the Hooker telescope is twofold. At its 134-foot focus, the increased scale of the crowded clusters makes it possible to select separate stars for spectrum photography, which could not be done with the 60-inch where the images were commingled. And the great gain in light is such that the spectra of stars to the 14th magnitude have been photographed in less than an hour. Faint globular clusters, then, will comprise a large part of the early program with the 100-inch telescope. The faintest possible stars in them must be detected and their magnitudes and colors measured. Spectral types must be determined, and the radial velocities of individual stars and of clusters as a whole. Spectroscopic evidence of possible axial rotation of globular clusters must be searched for, and the method of spectroscopic parallaxes, as well as other methods, must be applied to ascertaining the distances of these clusters. The possibility of dealing with many problems relating to the distribution and evolution of the faintest stars depends on the establishment of photographic and photovisual magnitude scales. Below the 12th magnitude, the only existing scale of standard visual or photovisual magnitudes is the Mount Wilson sequence, already extended by Sears to magnitude 17.5 with the 60-inch telescope. Extension of this scale to even fainter magnitudes, and its application to the faintest stars within its range, is an important task for this great telescope, as it will doubtless bring within range hundreds of millions of stars that are beyond the reach of the 60-inch. The giants among them will form for us the outer boundary of the galactic system, while the dwarfs will be of almost equal interest from the evolutional standpoint. The photometric program of the 100-inch, then, will deal with such questions as the condensation of the fainter stars toward the galactic plane, the color of the most distant stars, and the final settlement of the long inquiry regarding the possible absorption of light in space. Another research of exceptional promise will be undertaken, which is of great importance in a general study of stellar evolution, and that is the determination of the spectral energy curves of stars of various classes for the purpose of measuring their surface temperatures. A very few of the nebulae are found to be variable, and their peculiarities need investigation. Also, special problems of variable stars and temporary stars, and the spectra of the components of close double stars, which are beyond the power of all other instruments to photograph. Such a program of research conveys an excellent idea of many of the great problems that are under investigation by astronomers today, and gives some notion of the instrumental means requisite in executing comprehensive plans of this character. It will not escape notice that the climax of instrumental development attained at Mount Wilson has only been made possible by an unbroken chain of progress, link by link, each antecedent link being necessary to the successful forging of its following one. In very large part, and certainly indispensable to these instrumental advances, has the art of working in glass and metals been the mainstay of research. As we review the history of astronomical progress, from Galileo's time to our own, the consummate genius of the artisan and his deft handiwork compel our admiration almost equally with the keen intelligence of the astronomer who uses these powerful engines of his own devising to wrest the secrets of nature from the heavens. End of chapter 23.